Okay, now go ahead and get out your notes. And we're going to be at this part where we're going to talk about Hess's Law. So Hess's Law states that many reactions occur as a series of steps. So a lot of reactions that happen in the world and in our bodies happen as a bunch of little steps. So in order to calculate the heat of a reaction, sometimes we calculate the heat of each individual step. That's what we did in our lab last week. But sometimes we can manipulate different chemical equations and reactions to find the heat of an overall reaction or a much larger reaction that occurs as a series of steps. And I know this kind of sounds confusing, but we'll go through a practice problem. The key idea, though, is it allows us to determine the heat of the reaction without actually doing the reaction. So that's kind of nice. Okay, let's go to a practice problem. But first, I forgot. First, to solve this type of problem, we need to organize the given chemical equations where the total effect, so the net effect, yields the reaction that we need. We're going to have to manipulate a couple equations and cancel out some compounds that are not in our final reaction. And this is a key idea here. In order to cancel out compounds, we have to put the compounds on opposite sides of the yield sign. When one is a product and one of them is a reactant, that cancels it out. So, oh goodness. So, rules for Hess's Law. The reaction can be reversed. So whatever is a product, I can flip it and make it a reactant. This will change the sign of the delta H. So the change in heat will change if the sign will flip if I flip my reaction. The second thing is a reaction can be multiplied by a constant. The value of the heat will also be multiplied by that same constant. You can use any combination of these rules to get to your final answer. So this would be what our final answer is in this problem. We want to take these three equations right here, and we want to get them like this top equation. So we need to cancel out some compounds because not all of these compounds are in our final equation, and we're going to have to multiply some of them. So I always like to just start at the beginning. N2. If you look at that equation, we have 2 moles of nitrogen gas. So I see nitrogen gas down here. And the first thing that I notice is, well, nitrogen gas on the bottom right here is a reactant. And nitrogen gas in my final equation is also a reactant. So that's a very good thing. But in my final equation, I have 2 moles of nitrogen gas. And in this bottom equation, I only have 1 mole of nitrogen gas. So I write myself a little note and I say, okay, I need to multiply this equation by 2 because I need double the amount of moles. But when I multiply the equation by 2, I also multiply the heat of the reaction by 2 because it's like I'm going through that equation twice. So I'm going to get double the amount of heat. So then that's all I really see from that one. Then I'm going to actually save oxygen for last. And the reason I save oxygen for last is oxygen is here, but it's also down here. So anytime you see a chemical that's in 2 different places, that kind of should clue you in, I think I'm going to save that for the end. So now let's look for N2O5, dinitrogen pentoxide. Dinitrogen pentoxide is right here. Now there's a couple things that are wrong. First of all, in my equation down here, dinitrogen pentoxide is a reactant and I want it to be a product in my final equation. So to do that, I need to flip the equation. And so I also need to write flip over here because that means I'm going to change the sign from negative to positive. And in my final equation, I also have 2 moles of dinitrogen pentoxide. And in my equation on the bottom, I only have 1 mole. So I'm also going to need to multiply that equation by 2. And so I write on this side again, multiplied by 2. Because whatever I do to the equation, I also have to do to the heat of the reaction. The last thing that I notice in my top equation is H2. H2 is not in my final equation. There's no hydrogen gas in my final equation. So somehow I need to cancel out that hydrogen gas. Well, I notice I also have hydrogen gas down here, but they're on the same side of the equation. And in order to cancel them out, we need them to be on the opposite sides of the equation. So which one am I going to flip? Because I need to flip one of them. Well, I don't want to flip my bottom equation. And the reason I don't want to flip my bottom equation is because of this nitrogen gas. Nitrogen gas is a reactant in my bottom equation, and it's also a reactant in my final product. So I don't want to flip the bottom one. So I'm going to flip the top one, and we'll see if that takes care of my issue. So since I flip it there, I also flip it here. So now that I've written myself lots of notes, I like to rewrite my equations in the boxes below. So the first one, I'm going to flip it. So I now have 2H2O as my reactants, and that's going to yield 2 hydrogen gas and oxygen gas. And since I flipped my equation, I'm also going to flip my sign of my heat of reaction. So instead of negative 571, we get positive 571.6 kilojoules. So my second equation, I told myself I need to flip it and I need to multiply it by 2. So my products and my reactants are going to flip sides, and we're going to double all of their coefficients. So I now have 4 moles of nitric acid, and that's going to yield 2 moles of dinitrogen pentoxide and 2 moles of water. And since I flipped and doubled my reaction, I also have to flip and double my heat of the reaction. So I'm flipping the sign to positive, and when I double that, I get 153.2 kilojoules. Now my last reaction, I just need to double every coefficient. So we have 2 moles of nitrogen gas plus 6 moles of oxygen gas plus 2 moles of hydrogen gas yields 4 moles of nitric acid. Okay? And because I doubled my equation, I need to double my heat of reaction. So I get negative 696.4 kilojoules. So now comes the fun part. We need to make sure that all the work that we just did is going to actually give us our final equation. So we need to cancel out the compounds that are on opposite sides of our equations. The first one I see is 2 moles of water. I have it in the top in my reactants, and I have it in the next equation in my products, and so those will cancel out. Because in essence, we're going to add together all 3 of these reactions. And so anything that's a product can cancel out with any of the same substance that is a reactant. The next thing I see that cancels out is the 2 moles of hydrogen gas. It's a product on top in the first equation, and it's a reactant on bottom in the last equation. So those cancel. The next thing that cancels that I see is the 4 moles of nitric acid. It's there, and then it's there, so they cancel out. Now there's one more thing that cancels, but it does not cancel out completely. We have 1 mole of oxygen in our first equation as a product, and 6 moles of oxygen in our last equation as a reactant. So 1 and 6 don't cancel out, but it does cancel out one of them. So instead of having 6, we're only going to have 5. So now I'm going to rewrite everything that did not get canceled out. So we've got 2N2, 5 O2s, and 2 N2O5s. Okay, so if I write that down here, we get 2N2 plus 5 oxygen, I should call that 2 nitrogen gases, plus 5 oxygen gases yields 2 moles of dinitrogen pentoxide. Now, if we look at our original equation, that is exactly what it asked us to get to, so we know we did the work right. Now, the last thing that I have to do is, in order to calculate the heat of the reaction, I need to add together the heats of each of the individual steps. So when you put in your calculator, positive 571.6 plus 153.2 plus a negative 696.4, you will get 28.4 kilojoules. So we know that this reaction will absorb, since it's positive, it will absorb 28.4 kilojoules of heat. And we figure that out by doing the sum of each of the steps. Okay, let's do one more example. This one is not in your notes, so if you want to write it on the back, or actually don't write it on the back, just follow along. So here is the equation that we want to get to. Okay, and here are the given reactions, these 3. So again, I'm just going to look and see, let's just start with the first one. Carbon disulfide. Carbon disulfide, I see it down here, but it's on the wrong side of my equation. So what am I going to do to that equation? I need to flip it. I have the right number of moles, but I don't have it on the right side of the equation. So I also need to flip my heat of formation. Okay, the next thing that I see is that I have 2 moles. Let's see, the oxygens are, again, they're in different places, so I'm going to save this for the end. So I'm going to save that one for the end. And then carbon dioxide, this right here, it's already where it needs to be, and I already have the right number of moles. So this equation right here, I'm not going to do anything to it because I want my carbon dioxide to stay exactly how and where it is. So the last thing that I need to look at is sulfur dioxide. I see sulfur dioxide here. Now, sulfur dioxide in my equation that's given, it is already a product, which is good, but I only have 1 mole of it, and I need 2 moles. So I need to multiply this equation by 2, and since I multiplied that equation by 2, I also need to multiply that heat of formation by 2. So now that I've written myself all the notes and I've kind of analyzed the equations, I rewrite it down in my boxes below. So rewriting the first equation, I want to keep it exactly the same. Carbon plus oxygen gas gives me carbon dioxide gas. And since I didn't do anything to that equation, I don't do anything to the heat of formation. So it's still negative 393.5 kilojoules. Let me extend the page a little bit. My second equation, I multiplied by 2. So I'm just going to have a coefficient in front of all of them. 2 moles of sulfur plus 2 moles of oxygen gas yields 2 moles of sulfur dioxide. And because I doubled the equation, I again need to double my heat of the reaction. And so I get negative 593.6 kilojoules. Okay, my last equation, I said that I needed to flip it. So I'm going to make my products reactants and my reactants products. So I get carbon disulfide as my reactant yields carbon plus 2 moles of sulfur. And because I flipped my reaction, I now need to flip the sign. So it was positive, now is negative 87.9 kilojoules. Okay, so now's the fun part of canceling everything out. So let's see what cancels out. We have 2 moles of sulfur, 2 moles of sulfur. Those are going to cancel out. We also have a carbon, 1 mole of carbon here and 1 mole of carbon here. Those are going to cancel out. These oxygens are on the same side, and so they're actually going to add together. And so if I write down everything that's left over, I get carbon disulfide plus 3 moles of oxygen yields carbon dioxide plus 2 moles of sulfur dioxide. And if I look at my equation above and what it was asking me to find, that matches it exactly. So that's perfect. So now in order to calculate the heat of the reaction, we just need to add up these heats of formation. So negative 393.5 plus negative 593.6 plus a negative 87.9. When you add that up, you get a negative 1,075 kilojoules. So that tells us that this reaction would release 1,075 kilojoules of energy. So it's an exothermic reaction. Okay, so that's it for the examples. So now just a couple things that I want to tell you about. Next, this is homework number 4. It's on Hess's Law. You'll see that I set up the homework very similar to how I just showed the examples. So go ahead, and this homework is assigned. You will have a quiz on this homework, and that quiz will be on Thursday. So make sure that you come prepared on Thursday, and actually come prepared tomorrow to ask me any questions that you might have. So this is now homework. Next, the sub is going to hand out this lab, which is the heat of reaction for burning magnesium. This is the lab that we're going to be doing in class tomorrow. And so you need to do the pre-lab with whatever time you have remaining. So in order to do the pre-lab, you need to read it, you need to fill out a title, you need to fill out a purpose. You also, the new thing that you have to do this time is you have to fill out the materials you'll need in this reaction. Now I'll tell you that the materials that you'll need in this the materials you'll need in this lab are very similar to some of the materials that we've needed in other labs this chapter. So if you're feeling a little bit lost or confused, go back and look at some of the other labs that we've done. And then just like we've done in the last 2 labs, you will need a data table. So you need to draw your data table and you need to fill in anytime I say determine the mass or record the temperature. You need to write down what I actually want you to record. Remember, you're not going to have numbers yet because we're doing the lab tomorrow, but your data table needs to be filled out and ready to go before you come to class tomorrow. I will be doing a stamp, so make sure that these things are done. Title, purpose, materials, and data table. And so here, I just showed you exactly what needs to be done. Again, title, purpose, materials, data table. As you can see, I didn't draw it, so you need to have a nice data table, preferably with straight lines, not like I'm drawing, where you need to put mass of whatever. And then we will get these values in lab tomorrow. Perfect, thanks for listening, and you have the rest of the period to work on this pre-lab, and then if you finish this pre-lab, you can get started on working on homework number 3 or 4.